Right then, we're going to start another week and hopefully really are close to seeing you in school, okay? And then being able to answer all your questions on the statistics you've been doing and the mechanics you've been doing. So keep looking out for the information on that. In the meantime, keep track of all the questions you haven't asked. Now, lots of people are asking questions, that's really good. But if you still haven't asked them, note them down somewhere. And once you're back in, take the opportunity to ask them. Anyway, I'm going to go through the next examples from exercise 19, and they are the ones on equilibrium, okay? But they're equilibrium questions involving contact force, normal contact force. So the first one is this one that says a box of 16 kilograms rests on a horizontal table, so it's in contact with a surface. It's on a surface, and there are 4 strings attached with these forces in the strings, okay? First thing I'm going to say is that's the only diagram they draw in the book. It's a rubbish diagram. We need to do better than that. So the diagram should have been this, okay? Don't ever leave your diagrams like the one in the book. The diagram, I'm just going to rub out the highlighting there. Oh, can I rub that out? Perfect, I can do it, good. And that highlighting there. The diagram should have looked like this. 1, 2, 3, 4 forces to do with the strings, and you absolutely have to mark in the weight, and because it's on a surface you have to mark in the normal at right angles to contact force. Without those other 2 forces, none of this makes any sense, okay? I would also make that note there next to it. It's in equilibrium. What does equilibrium imply? It means everything balances, up with down, left with right, up the slope with down the slope, north and south, west and east, balance in these opposing directions. Now in this case, if we balance horizontally, we consider these 3 forces, and I would simply have left, so going to the right, balancing going to the left, and we get that the tension in the 4th string is 5. If you balance the forces upwards, then we are balancing only these 3 forces. Now notice in this book, all the forces are perpendicular to each other. One of the things we're going to add next year is a simple bit of right angle trig. If you've got forces at an angle, how we work with the components. And that's going to be a crucial idea for the projectile work and for this work on the forces. Anyway, when we balance the forces upwards, we get the 2 upward forces balance the downward force. Use 9.8 in this question and you get 140 newtons to 2 sig fig. Why 2 sig fig? 2 or 3 would be, no, actually 3 wouldn't be fine. Everything in the question is 2 sig fig, isn't it? There's no inconsistency in anything they use. Even G is 2 sig fig, so 2 sig fig is the appropriate thing. Right, the next example. A toy of 320 grams, so 0.32 kilograms, rests on a surface. Someone pushes down vertically on it with a force of 8.2. There's a string and the string is pulled vertically, and G is 9.81. Give your answers to blah, blah, blah. Right, the starting point has to be a diagram. And as soon as we've talked about a surface, we need a normal reaction and we need the weight, with G standing for the acceleration due to gravity. Notice on my diagram, all the arrows start at the object and then leave it, okay? So all the arrowheads are, you might think this is a small thing, but sometimes small things are important. All my arrowheads are here. They're not getting lost on the diagram. Okay, and I've also made that comment is in equilibrium. As soon as I've made the comment about equilibrium, I can balance the forces. So express the normal reaction force in terms of T. That was the question. What on earth do they mean by that? Well, I don't know. What I'm going to do though is I'm going to do the only thing I can, which is balance vertically. T plus R is equal to that. Oh, and I know 8.2 and I know 0.32 G. So I can write, all right, I can write R in terms of T. I can express the normal reaction in terms of the tension. The normal reaction will be 11.34, take the tension. Right, the smallest value of T required to lift the toy off the table. If the toy leaves the table, it loses contact. If it loses contact, there is no contact force. We are talking about the moment when, oh, it's just gibberish there. Right, ignore all of that. I don't know what I was thinking when I wrote this. Clearly not late. You can see the sunshine out there. We all make mistakes, except Mr. Holloway. Therefore, if there is loses contact, the reaction force is 0. If the reaction force is 0, the tension is 11.3. 11.3 is the smallest value to 3 sig fig that the tension would be in order for the reaction to be 0, okay? Loses contact is reaction 0. No contact force. Right, in the next part of the question, we've got find the acceleration when t is 12. So let's make the comment. Because t is bigger than 11.3, there is no contact force. There is no equilibrium. So if there's no equilibrium, it's Newton's second law in the direction we're applying it. So 12 take 8.2 take 0.32 g. The girl's still pushing down on the object. The object still has a weight. It's the reaction we don't have, because we know that 12 newtons is enough to make it lose contact. No contact, no reaction force. And that's equal to mass times acceleration. That gives an acceleration of 2.07 meters per second squared. So even in this section called further equilibrium questions, there might be some acceleration questions. Newton's second law. Right. Whatever you do, though, don't make the mistake I made partway through that question. I think we recovered it. I don't think anyone noticed. Right. The next example, a box of 1.2 kilograms is pushed into a wall. And it's not just a wall, it's a rough wall. Okay? And it's pushed with a force of 40 Newton and rests in equilibrium. Right, so let's draw a diagram. A diagram has a vertical wall, an object in contact with it being pushed into it. So I would have 40 newtons that way, so I can see the arrowhead. A reaction with the wall at right angles to the wall going that way, so I can see the arrowhead. The object was not suddenly in deep space. It has to have a weight. Now, that comment about equilibrium and the mention of the word rough means there's a second contact force which is parallel to the surface, and that's friction. And if you look at the diagram now, 1, 2, 3 forces, it couldn't possibly be in equilibrium unless there was this force acting up the wall, the friction. The frictional force, the force that's stopping it sliding down, so the frictional force acts up. Right, it's in equilibrium. So horizontally, the two horizontal forces must balance. R is 40. Vertically, the two vertical forces must balance. So the friction is 12 newtons to 2 sig fig. Why have I chosen 2 sig fig? Is it because the book did? The book does. I mean, in this case, though, we've got 3 sig fig, we've got 2 sig fig, we've got 2 sig fig. They'd let you away with 2 or 3 sig fig. That's all you need to do for this part of the question. However, if you want a glimpse into the future, ooh, time travel, next year, if they talk about limiting equilibrium, if we're told the box is on the point of sliding, if we're asked for a minimum value of the roughness, we're going to talk about a measure called mu. It's a Greek symbol called mu, and mu will be the relationship between reaction and friction. Okay, the value of mu will tell us the maximum value of friction in a given circumstance. So mu is the ratio of friction and normal reaction when the equilibrium is limiting, but that's for next year, okay? So 0.3 would be the minimum value of mu for equilibrium this time. It's the top bit, which is relevant for this year, but I can't remember if the physicists talk about mu. Right then, that could be a record for me. It's under 15 minutes, so what do I want you to do? In all these questions, it's the same method for all the mechanics, doesn't matter what topic it is. Read the question, diagram. In this case, it's draw a diagram of forces, a big, clear, unambiguous diagram. If you've got to include acceleration, double-headed arrow off to the side, but on all my diagrams, the force comes from the object away, so you can see all the arrowheads. If we've got to put velocity on, the velocity is marked to the side, single-headed arrow. Acceleration measured to the side. And on that diagram, I might mention whether it's equilibrium. I go through any important things. Is the string light? Is the surface rough? Blah, 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 blah. Read question, draw diagram, reread question, check everything's on a diagram. If the question talks about equilibrium, it's talking about balance. Left with right, up with down, north with south, balance. So if it says equilibrium, you write what direction you're working in and balance forces. If the forces aren't in equilibrium, it's Newton's second law in the direction of acceleration, because if they're not in equilibrium, they're accelerating. You might be then using Suvat to finish. Once you've got an acceleration, you might be using Suvat, or you might have used Suvat to find the acceleration. So Newton's second law in the direction of the acceleration, perpendicular to that, balance the forces. So equilibrium, balance, balance. Not in equilibrium, Newton 2 in direction of acceleration, balance. Right, note these crucial methods, because that is all there is to it. That's what makes physics so easy, the fact that it's a few simple ideas. 19C only has got 8 questions. I've left you 45 minutes by the end of this, so I would make notes, do as many questions as you can. What's coming next, and I still can do this before 50 minutes, we're left with connected particles and pulleys, which are connected to each other, and they simply use all the ideas we've used up to this point. So there's going to be equilibrium, there's going to be Newton's second law, there's going to be Suvat, and there's going to be the forces. And then hopefully we're going to see you, okay? And even I'm missing you at the moment. Take care. See you soon.